Okay, so for the free body diagram, we have okay, here, this is the ball. We have FG pointing downward, and then from the second diagram we can see that the ball is at an arc, not a flat spot, so Fn we point it at an angle, right? So this is Fn, and that's of the forces. For part B, Fn, I'll look in the y direction, so I'll draw the diagram again. I'll reference this as my angle, then the ball is right down here. It has a height of d as given in the second diagram, and then I'll treat the radius as r, or this leg as r, and then the hypotenuse as capital R. And then we know that this length is Fn, this is Fnx, then this is Fny, right? So F is equal to ma, but then it's traveling in a horizontal circle, so it's not slipping up or down, so we know that the net force in the y direction is equal to 0. So in the y direction we got Fny pointing up minus Fg pointing down is equal to 0. Then Fny is just the adjacent side, so that's cosine. So you get Fn cos theta, and then I'll move Fg on the other side, and then I'll expand it, which is just mg, right? And then we don't know what theta is, and we need to use R and D. So we know that cos theta is equal to adjacent, which is D, over the hypotenuse, which is R. So I'll replace that with what we have. So Fn D over R is equal to mg, right? And then divide both sides by D, and then multiply by R, which give me this equation for Fn expression. mg capital R over D. So to find V10, we have to look at the horizontal forces with Fc and centripetal acceleration with V tangential in it. So we know that net force in the x direction is equal to Fc, right? It's pointed toward the center of the circle. So I'll redraw the triangle. So we have this. And then this was my reference angle. This is lowercase r d for the height, and then the hypotenuse is capital R, right? And then Fn, Fnx, and then Fny, right? So Fn in the horizontal, there's only Fnx. Then expand on Fc as mv squared over lowercase r, right? Radius of the circle. Fnx is opposite, so that's Fn sine theta to mv squared over r. Earlier we found in part B Fn to be mg capital R over lowercase over d. So I'll plug it in. So you have mg capital R over d sine theta to be mv squared over r, right? And then sine theta is equal to opposite, which is lowercase r over hypotenuse, which is capital R. So I'll plug it in for sine theta. So mgr over d, capital R over d, times lowercase r over capital case R. right? So capital R cancel out, leaving you with mg lowercase r square over d is equal to mv squared, mv squared of r. Then mass cancel out too. So you get this v equation, v squared is equal to gr squared over d. But then we want it, there's no lowercase r, but in capital R, so we know that in our triangle is the hypotenuse, capital R squared is equal to the legs square plus another leg square, right? So it's d squared plus lowercase r squared. And then if we move it around by subtracting d squared on the other side, we get r squared to be lowercase r squared to be capital R squared minus d squared, right? So I'll plug that capital R squared into this. So v squared is equal to g capital R squared minus d squared over d. Then square root both sides, which give me this equation. But then in their given equation is y. So looking at the second diagram, we would assume that d is equal to y, right? So I'll replace all of my d with y. So v is equal to radical g r squared minus y squared over y, and that should match the given equation. So in part C, we found that v is equal to radical g, then capital R squared minus y squared over y squared. Over y, right? So to find the angular velocity, we know that v is equal to omega lowercase r. So we just plug in v into that. So omega lowercase r is equal to radical g r squared minus y squared over y, right? And then we draw the diagram. Reference angle is right there. The r lowercase r and then capital R. And then earlier in part C, we found that r squared is equal to capital R minus d, capital R squared minus d squared. And then we know that from diagram 2 that d is equal to y. So r squared is also equal to, lowercase r squared is equal to capital R squared minus y squared, right? So let me square both sides, which give me with this equation. That. Then I'll plug in r squared with what we found over here. Square. Lowercase r squared with what we found. So the parenthesis would cancel out on both sides, leaving you with this square root both sides. So the angular velocity is equal to square root of g over y. So in part D, we found that omega is equal to radical g over y, and then y is a constant, so we can ignore it, right? So from looking from this equation, we know that w and y are inversely proportional, right? So if you want omega min, then your y has to be really, really large because they're inversely proportional, right? So when omega is small, your y has to be large, right? So from the diagram, your y can be like the whole radius, right? So this whole height, if this whole height represents your y, then it's the same as this length, right here. And this thing is R, so your Y has to be R. So that means your Y is equal to R in omega mean. So omega mean is equal to radical G over capital R. And then we don't want radical R on the bottom because it's improper. So we'll multiply top and bottom by radical R, which leave us with this equation. So radical G times radical R is radical GR. And then on the bottom we have radical R times radical R, which is just equal to R. And it should match what is given. Okay, so for part F, we want angular velocity in rev per minute. So we know that our R is equal to 0.20 meter. And then our so if the bar is halfway up, we know that Y is equal to R over 2, right? Because that's what's Y stand for, the height up. And then that should be 0.2 meter over 2, which is 0.1 meter, right? So we know that angular velocity is equal to radical G over Y. And I'll plug in the number 9.8 over 0.1, which is 9.9 rad per second. But then we want rev per minute, so we'll do some unit manipulation. So number 9 rad over second. Okay, so 2 pi is equal to 1 rev, so the rad cancel out, and then 60 second is equal to 1 minute. This should give us 94.5 rev per minute. And then for part G, we want an expression for t period. So we know that v is equal to the distance, or in this case speed, is equal to the distance over time. So that's just, so it's just v is equal to 2 pi r, which is the circumference of a circle, over the time period, t period, right? Then move t and v around to get this equation. Right, and then we know that v is equal to omega r, so I'll plug it in. And then r cancel out, lowercase r. So you get t is equal to 2 pi omega. And then earlier we found that omega to be radical G over Y. So I'll plug it in for omega. Since this is a fraction on the bottom, we'll flip it over to get this equation. Two pi, and then radical y over g. And then that's our t expression. Okay, so for this problem, I'll reference the ball, right? So using the same triangle, right, we're given, like, this is D, this is lowercase r, then the hypotenuse is capital R, okay? And then this is Fn, Fnx, then Fny. We're given a an angle. So in the y direction, so we have f is equal to ma, but in the y, it's not slipping up or down, right? It's going in a horizontal circle. So we know that net force in the y direction is equal to 0. So pointing up, we have F and y, minus pointing down, which is this gravity, Fg. is equal to 0. Fn y is adjacent, so that's cosine. So Fn cos theta. I'm going to move FG on the other side. You get this, right? Plus FG. So your Fn is equal to Fmg over cosine. Right? So now we're trying to find the angular acceleration use referencing the ball, right? So the only way to get angular or v or v linear or angular acceleration is looking at FC. So we know that the net force in the x direction is equal to FC, right? Because the force pointed toward the center of the circle. And then the only force in the horizontal is Fnx. So Fnx is equal to FC. So Fnx is opposite, so that's sine. It's equal to mv squared over r, or lowercase r, right? Radius of the circle. But then we know that v is equal to omega r, right? So we'll plug that into here, into v. So Fn sine theta is equal to m omega lowercase r squared over r. Then Fn sine theta is equal to m omega squared r squared over r. One of the r cancel out, leaving you with this. Fn sine theta is equal to m omega squared r, right? Omega should be the same because they're covering the same theta in the same amount of time. So omega is the same for the ball or the bow. But then we're referencing the ball in this problem. And then I'll plug in Fn. So you get mg sine theta over cosine theta is equal to m omega squared r, lowercase r. Then mass cancel out. So you get omega squared r g 10 theta, right? Sine of cosine is 10. Divide by r. Right. So you get omega squared is equal to g 10 theta over r, and then square root both sides. So our final equation is omega is equal to radical g 10 theta over lowercase r. But then we don't know what lowercase r is, so we have to find a replacement for it. So I'll just move to another page. So I'll redraw the diagram. So this is lowercase r, this is d, and this is capital R. Right? And then our angle is right here. So we want in terms of capital R. So we have sine theta is equal to opposite, which is lowercase r over r. So multiply r, capital R, where we get this equation. Right? And I'll plug it into r, lowercase r. So omega is equal to radical g. I'll expand 10 to be sine theta over, and then lowercase r become capital R sine theta, and then cosine theta from 10. The sine cancel out, leaving you with this equation. Oops. G over capital R cos theta.